Hey everybody, welcome to another CS302 assignment video. For assignment 3, we're going to be implementing sorting. Specifically, we're going to implement bubble sort, which was not exposed too much in CS302, but I'd imagine in CS135 or CS1, you were exposed to bubble sort, and then you have to also implement merge sort as well. So for the assignment, you're going to have to use the linked list class you had from assignment 1. So you have to make sure that the linked list class from assignment 1 was working, specifically that swap function, which may be used in a few spots in assignment 3. You want to make sure that's sort of correctly working. Although from assignment 1, all of the test mains, it tested out all the possible edge cases. So if it worked for assignment 1, you should be okay for assignment 3 with the swap functions. If not, you're going to have to spend a little bit of time working on getting swapping to work. So in the assignment, you're going to have to use your linked list .h and linked list.cpp from assignment 1 to implement two main files. So first one, you're going to have a file called bubblesort.cpp where you want to include ll.h in that file. And in that file, you will essentially read in an input file of integers through a Linux redirection, and you want to populate a linked list of integers with that file, and then bubble sort using bubble sort from assignment or from your CS1 class, but you have to, of course, modify it to work for linked lists. So I do provide you with some references here. So bubble sort and merge sorts. I have used two Geeks for Geeks references, which are good references to have, but you have to modify these two to work with linked lists. So that's going to be the real trick, is getting these to work for linked lists. Then you have to also implement merge sort.cpp, which of course you implement the merge sort function or merge sort algorithm. So how you set up your mains are up to you. There's no restriction as to how to do it. But a few restrictions are you have to, of course, use a linked list class. You have to maintain a linked list of integers. And you cannot have any counter control loops because you don't need to, because a linked list, you start from the beginning, when you hit the end, you're done. You can have for loops, but they cannot be counter controlled. So you have to use iterators to navigate through your linked list, do comparisons, swaps, and so forth. So I'm going to just sort of give you an idea of how to get started with these sorting algorithms. I'm also going to go over a little bit as to how Linux redirection works. So in this PDF right here, you can see at the very bottom, this is actually how you redirect the input. So you're going to be using cin to read your input, but this symbol before the input file right there is going to force cin to read from the file versus just from the terminal. It's just a way to redirect the input from your terminal to a file. So cin will read from the file is the idea. So let's go ahead and just walk through a little bit as to how to implement these two sorting algorithms. Okay, let's go ahead and discuss bubble sort first. So you can imagine that, let's say you have this list of integers, 3, 2, 5, 1, 4, and imagine the input file, you would have just a set of integers in the file. You'd have possibly one integer per line, so 3 followed by a new line, 2, then the new line. So you have really 3, 2, 5, 1, 4, each integer on its own separate line. Use a standard end of file controlled loop, but remember cin is going to be like your file stream because you're using redirection. And we just simply push back 3, push back 2, push back 5, 1, and 4, which of course creates that linked list right there. Now in this file, you don't want to have any counter control loop, but of course you can use all the iterators you like. Now here I used auto because it just makes it easier to define variables, which is not required really, but you could, of course, you could have ll int followed by the scope operator iterator. That works, but sometimes auto can be a nice workaround. That's up to you how you want to do this. Of course, auto can be sometimes not the best for readability purposes, but I mean, in this case, we kind of know what I and j will be used for. They're going to be iterating through our list, so auto is good enough. So right here, I set I to the beginning of the list, and then I have j set to plus plus list.begin, so j is going to be the second element in the linked list. Now, bubble sort, the way it works, remember, we always compare adjacent elements. So, of course, we can do something like, so if, let's say, if star j is less than star I or something. So this is the case, element to the right is smaller, so then we have to swap. So if this happens, we would just simply have our list object dot swap I comma j. So the end result, now of course, remember how swap works, it's going to physically lift up these two nodes and move them. But to make life a little bit easier, I'll just sort of shortcut this and just do, I'll put put 2 over here and then 3 over there. So those two would have swapped. And then we want to increment I and j one to the right. So we do I plus plus j plus plus, so then they both move over. So I now here, j is now there. And same idea, we just compare the two. In this case, we're not going to swap because 5 is in fact larger. We then move I and j, you do I plus plus j plus plus to move them both over to the right, like so. And then right here, we would compare. So since j is smaller, we would then of course swap these two. So you would put 1 right there, and then 5 right here. We would swap these. Of course, we wouldn't swap data fields. We would swap the two nodes, but to kind of make this trace doing the video go by a little faster, we can imagine you would actually physically swap those two nodes. Then, of course, we move I and j over to the right once more. So now I goes over here, j goes right there. And again, we have to now compare the adjacent elements. So since j is smaller, we would then swap these again. We would call a swap function, pass an I and j respectively, which of course would adjust. So you put 4 over here, and then as a result, 5 goes to the very end. And then of course, now we would move I and j over to the right, but now what's going to happen is I is now at the end, j is going to be at null, so we stop. So in our first iteration, what's going to happen is once I hits the end, we're done. And the result is the biggest element bubbled all the way to the end of our linked list, hence the name bubble sort. So I'm going to go ahead and put a threshold here, which means now for our next iteration, remember we have a nested loop we have for bubble sort. Next iteration, we're going to stop a little earlier this time because in the first iteration, we had to bubble all the way to the end. But next time around for this iteration, we're going to bubble all the way until we reach this location in our linked list. So same idea. We're going to have I right here. And then again, we reset j to right there. This could be kind of done in the outer loop. We can just reset I to the beginning and j right after the beginning. And then we have I and j as adjacent nodes. Then we do the same exact procedure. We compare them. The j is not smaller, so we don't swap right here. So we move I and j over to the right. We again compare. So since star j is smaller, we have to swap these two. So I'm going to use blue here to sort of symbolize the difference. So we're going to swap these. So now what happens is 1 will go here, and then 3 will go right here as a result. Then we're going to move I and j over to the right, like so. We again compare. So since star j is not less than star I, we don't swap. We move I and j over, but now I reached that node right before that threshold. So at this point, we stop. We don't have to iterate any further. So now we're going to move this threshold essentially 1 node to the left. And then we again reset I and j and so forth. This threshold bar, in a sense, could be possibly an iterator that kind of points to the location in our linked list where the inner loop is going to stop. So once I hits that iterator, we know we want to stop right there because we hit the kind of end of the unprocessed list, because right here, everything after that red line, that's our processed list. So we can have an iterator that points to a node. Either it could point to the 3 or to the 4, wherever you want it, depending on how your logic is set up. But you want to have an iterator that tells you that once I reaches that spot, we know we can stop the inner loop at that point. And once this line reaches the very front of our list, then we're officially done. Then bubble sort is finished. So basically, we have this nested looping structure. The outer loop essentially always moves that bar from right to left, one node at a time. The inner loop is moving the I and j and then constantly comparing the adjacent nodes and then swapping or not swapping accordingly. So that's your bubble sort basically. So the code for the bubble sort essentially is doing this in a way, but again, we don't want to use um, integers or counter controlled. We of course have for loops, and once your iterator equals a certain threshold iterator, we can stop at that point, but you want to make sure we don't have any counter control loops in our program. So that's going to be your bubble sort. So the only hard part is making sure the swapping works. But luckily for assignment 3, only the adjacent swap has to work, because you're only going to be swapping always adjacent nodes, since I and j will be adjacent to each other. So it does kind of help with some cases. However, there can be a case where you're swapping, let's say the very first pass, I could be second to last, J could be a tail node, so you want to make sure that that edge case is handled. That's the only edge case you have to really consider. And also at the beginning sometimes, when I is at the very front and J is after, when you swap the very first 2 nodes potentially, you could have to make sure a head is reassigned to the new front. But that's basically bubble sort right there. So let's go ahead and now discuss merge sort next. Okay, so let's go over merge sort for a second. So I guess there's going to be some degree of having a counter control loop, but the only time you can really do it is just in the merge sort function. So for merge sort, imagine you're given some linked list, and for the merge sort function, you're typically given like a left and right endpoint. So here, left and right wouldn't be indices, those would be possibly iterators that would tell you what portion of the list you're going to be processing. So remember, for merge sort, if you recall this from the lectures, you have to compute the middle position. But linked list, it's not really obvious what the middle position really is. So you'd have to actually create some iterator. So you could do something like have like maybe auto I equal left. So left and right would be just parameters in the function. And you have to just iterate one node at a time in this linked list until you finally hit the right position. And it maintains some counters. So you count how many nodes you have. So, okay, so in a sense, this is the only spot really where a counter control is going to be okay, because really there's no other way to actually do this. So right here, we first have to count how many nodes we have. Once we iterate every node from left to right, we maintain a counter. We take that counter and divide it by 2. So now we have the half of, so we know the half size of this linked list. Then we have to iterate the linked list once again, and this will be the only counter control loop part. You want to, of course, go size divided by 2 number of iterations, and maybe use the I iterator once again, reset it to the beginning, and then just iterate the size you computed earlier divided by 2. So you compute I to be right here in the middle somewhere, and you stop. So at that spot, okay, fine, we have a counter control loop of some sort to determine the mid position. Now for merge, remember what happens now. We have to now just call 2 recursive function calls. Okay, so first function call, we can just call merge sort function, pass in, I'll call it list. You can pass in left, you can pass in I. That will magically sort the right half. Then of course you can call merge sort on the, that will merge sort the left half. Now you can merge sort the right half by passing in the list. I would say maybe actually first do I++, before this function call happens, you pass in I, pass in right, which will then sort the right half, essentially. So you pass the iterators in so you know exactly what portion of the array is going to be processed. So essentially, in this function call, left will be the leftmost position, I will be the rightmost position of this left half, and the right half is going to be after I. So this I is going to be the leftmost position of the right linked list, the right half linked list, and then right will be the right endpoint of the right half linked list. Now, of course, you have some base cases to consider. So let's say if left equals right, you have a size 1 linked list. So, of course, then you want to return immediately. So, there's a few checks to consider. So, after that, what you want to do is you want to now, once you have the two sides sorted, you have to now essentially run this merge step. Let's go ahead and sort of discuss briefly how do we actually sort of merge with linked lists. Okay, so for the merge function, I mean, there's really two scenarios. So again, I'm not going to tell you exactly how to implement this. So you could have your original big list and have your three iterators left, right, and then that I iterator in the middle. Or what you could have is, in some cases, you could just have two individual linked list objects which represent the left and right half. So it's up to you how you set this up, but I'll just go with this approach. Since this is kind of similar to how the array version works, but again, it's up to you. But in this case, you can of course can create two temporary iterators, but I'll call them A and B, where A is set to essentially B. Oh, sorry, A is set to left, and then B would be set to index I, and of course you do B++ to move it over. So then B would be the first node in that right half, and then A would be the first on the left half. And all you have to do essentially is just once A and B are both beyond their respective bounds, once A goes beyond I and once B goes beyond right, then of course you're done. But in the meantime, what you can do is just simply just do star A and star B. And the smaller of the two, you just simply have to push back. So here, I'll just give you an idea. You can just do something like if star A, say less than equal to star B, then maybe you can define a local linked list object within this function. So possibly you could have like ll int, and I'll call it sorted list, because it's going to be the sorted after we merge the two sorted halves. So you can of course can say if star A is less than equal to star B, you can just do something like sorted list dot push back star A, and then do A++. And for the else case, you would just do sorted list dot pushback star B, and then B++. Then of course, once, then you can have these additional loops. So if you look at the code for the merge function in Geeks for Geeks, you have those additional while statements at the very end where those are mostly designed for, because you can have a case where if I goes beyond its bounds first, you just copy the remaining elements in that B array or vice versa. So you have to do all that. Once you have your sorted array, well, there's two things you can do. Once you have your final result, you can just return sorted list if your merge function just returns. But if you're going to copy the Geeks for Geeks approach, then this array would be a pass by reference. So you can, of course, just deep copy everything in sorted array into your list, into your reference parameter, which will just override the reference parameter, and then now list would contain the merged of the two halves, and then you're done. So it's up to you. So you can return the sorted list back to merge sort function, or once you have your sorted list, so if your parameter that's being passed into the merge function is just called list, you pass in left, I, and right, you could just, have list equals sorted list at the very end, which will just simply deep copy sorted list into list, and then now list is going to be the final sorted product. So again, the idea is not so difficult, but the challenging part is to convert this code into using linked lists. So you don't want to have any counter control loops except for the merge sort function where you have to determine the middle position. Without a counter control, I just don't think it's possible. That's the only time you're allowed to actually do that. Okay, let me go ahead now to show you the simple input output and how to compile the program and so forth, just to give you an idea. Um, if in case you haven't used Linux redirection before, I'll give you some, just show you how that actually works. Okay, so let's go ahead and just first take a look at our input files we're going to be working with. So here's the very first, very simple one. So I'm going to just use Vim to display the file right here. I guess I use a cat command, but I use cat, I guess, instead, cat, to display this. So input01.txt, and there's the actual file that's given to you. So you can see instead of integers, it's going to be line separated. So you can use easily the input operator or the extraction operator to read each number one by one. So you'd read 4, push back 4, read 4, push back 4, read 4, push back 4, read 5, push back 5, and so forth to construct your linked list. So to compile your program, so remember, you want to use the ll.h file from assignment 1, so you have to, of course, include ll.h in your bubble sort and merge sort function, files. So when you want to compile, you just do g++ ll.cpp and then bubble sort.cpp. Now, if you do this, it creates a.out file, but if you want to create a separate exe bubble sort, you can use this -o flag and then just do, I'll call it b sort. So now this is going to be your a.out in this case. Okay, so it compiles. So I would do /b sort. And now to give our input file, we're going to just use this symbol, the angle bracket that kind of points towards the exe file. And I'll pass it input 0, 1. So all you have to do is write end of file control loop, but you're going to treat really cin like your file stream. That's what this allows you to do. Now cin is going to read this file versus reading from the terminal directly. So that's what's going to happen here. So it's going to just simply, our program will read in this file, and we're going to just run a bubble sort function, and then we're going to output the sorted list. And there we are. And we also have our other files as well. We have bigger files we can also use. So if I were to output, let's say, input 0, 2, we have a bigger file over here. So of course, I think the 100 integers. So of course, we can do the same idea. So I'm going to go ahead and just clear this. And let's go ahead and rerun this. So /bubble sort, pass in input 0, 2.txt. And you can see that the result would be a sorted array. It cuts off on the bottom, unfortunately, but you can just sort of, I guess, sort of for now, just believe me that this is actually sorted correctly. But I have an ultra-wide monitor, and this program, what's this called? What is this program actually called even? OBS Studio, there we go. OBS Studio can record the entire screen, but it gets enough. Okay, so we also can do the same thing for merge sort. We can do g++ ll.cpp merge sort.cpp, and again, if you don't want to have a.out, you can do -o, and I'll call it m sort for merge sort /m sort. I'm going to pass in my input file, so now my cin is going to read from this input file, outputs a sorted array, and do the same thing for input 2. And we can see how the output did sort, or at least it looks like it's sorted correctly. So there we are. That's how you run this, but again, just make sure you include ll.h in both main files. I will provide to you kind of these main files, but of course you have to fill in the blanks. I probably will include the ll.h file in here as well, so that way you don't have to worry about including it. It will be included for sure. So Once you're done, you want to submit everything to code grade. Now, for code grade, I actually have it set up so we're using a different version of the auto test. So code grade has a new version of this. So there won't be any there won't be any header comments to check for, only general comments only. But everything else in your case should be the same. You drag and drop your files. You want to drag and drop your ll.cpp, merge sort.cpp, and bubble sort.cpp. Drop those files in the code grade, submit those or hand those in, and it will right away compile and then run with several these. I have 3 input files to test for, so we'll just run all those for you, and then that's pretty much it. So hopefully this video I guess helped sort of give an idea of how to implement these 2 sorting algorithms. So I guess happy coding, and till next time.